In our last class, we used Python to plot mathematical equations. So here let us take it a little bit further by plotting different graphs to study various phenomena like beats, amplitude modulation, and three-phase AC circuits. So first of all, let us take the case of a three-phase AC circuit. We know that our line voltage for a single phase is 230 volt RMS, and for a three-phase AC between two phases it is something like 400 volts, that is root 3 into 230. So let us plot the graphs and see how this voltage arises. So first job is to plot our AC waveform, that's our line voltage. So let us write the code for that. Again we just import the plotting and the numpy package, make a linear space, a time is equal to space. So we want to see the voltage, say for something like say 0.1 seconds only, because 1 second there will be 50 cycles, so we will watch only 5 cycles. Say take 500 points, and the sine wave, suppose the phase 1 will be 230 into square root of 2 into sine 2 pi. What is the frequency? Frequency is 50 Hz, and into t. So now we can say plot y1. So this will show the single phase AC. Let us say this is AC dot py. Save it as AC dot py and say Python AC dot py. So we have, see, up to say 0.1 seconds we have 5 cycles because it's a 50 Hz AC. Now let us add one more phase, that is only change will be the second one will be 120 degree out of phase. So 120 into pi by 180, converting this 120 into radians. Then we'll plot both this, say y1 as well as y2. And if you measure the voltage between these two using a meter, what you are measuring is actually the potential difference. So you will also plot, say, y2 minus y1. So save this and run it again. So here you can see the phase 1, the blue, and this green is this second, so it's already starting at 120 degree, and the red is the difference between the voltage difference between two phases. So you can easily see that at any point, because the phase difference, the voltage is more than any single phase here. So this is a very simple demonstration of, like how you get a higher voltage between two phases. So you can just visualize it in Python by few lines of code. Now let us make another sine wave. Say we'll make it for a higher frequency. Suppose say frequency is equal to 100 Hz, and amplitude just take it as 1, so 2 pi, and frequency put here. So we have 100 Hz, and also make one more, that is say 104 Hz. Okay. So here frequency is redefined as 104, so you have two waveforms. Let us plot these two, 100 Hz and a 104 Hz. Now this is how it looks. Now what will happen if you add these two sine waves? So just add them together, y1 plus y2. So this is not enough cycles, so let us put, say, something like, look it for half a second. So what you see is, adding these two sine waves with some frequency difference, beats are formed. So there is a 4 hertz beats. How do you know this is 4 hertz? So one cycle, see some here, you can find out this frequency from this time interval. So 4 hertz beats are formed, and if you want to see this, say make it 10 hertz and see how the envelope frequency changes. Now you can see that when the difference is more, the frequency of the envelope is changing. There are more envelopes, so you can see that in 0.5 seconds there are 5 envelopes. That means there is a 10 hertz is the frequency of this envelope. This is how beats are formed. And now we'll make a small change here. This is 100 hertz and I'll make it 2 hertz here. So you have 100 hertz and as well as a 2 hertz, and what we do is the product of these two, and this is a typical case of an amplitude modulation. You have a carrier frequency and the signal frequency, and they are multiplied, and this is how amplitude modulation is done. So the result will look like this. See, amplitude modulation. But let us plot the signal also, say t and y2. So you can see how the amplitude modulation changes with signal. You can see when the signal is maximum amplitude, the modulated wave also has maximum amplitude. When the signal goes to 0, this goes to 0 here. So there are numerous examples of plotting like this. Let us take something slightly different. Let us do a little bit of computation, and for that we'll choose one of our very familiar problems, that is a spring, one end fixed, and we attach a mass to the other end, and if you stretch it slightly from the equilibrium position and release it, it will start oscillating, and we know that it is executing simple harmonic motion. That means the moment, the displacement as a function of time should be a sine wave. So how do we calculate that? Only thing we know is we just start typing whatever we know. Suppose there is a spring constant, so let us take it as some value 10, and mass, let us take it as 1, and then we also have to start the initial position. So initial time t is equal to 0, and we also define a delta t, that we take it as say 0.1, and this I'll explain why this delta t is done, because what we are going to do is at t is equal to 0, we know the velocity is 0, and displacement, suppose say we are stretching it by 2 cm, 2 units when t is equal to 0. So that means spring is, the mass is pulled by 2 cm and just released when t is equal to 0. So all these initial conditions are known. Okay, so now the procedure is, let us calculate the velocity and the position after delta t, that is 0.1 second. How do we calculate that? Like, the velocity, initial velocity is known, so we have to add something to find out the velocity after a time delta t, right? And to do that, first we have to know the force. Force is equal to minus k into x. This is the equation, right? Force is spring constant into displacement. This is given to us in this problem. So force is there, and we also know that acceleration is force by mass. So acceleration A is force by mass. And what is acceleration? Acceleration is dv by dt, right? A is, let us write it here, A is equal to dv by dt. This implies dv is equal to A into dt, A dt, right? A into dt. So A multiplied by dt. So v after a time dt is v plus dv. And what is dv? dv is equal to A dt, A into dt. So simple equation, because we know the velocity, this is the velocity when time is equal, t is equal to 0. So after a time interval delta t, v will be this initial velocity plus acceleration into dt, and acceleration is nothing but force divided by mass, and force is equal to minus kx. And we also know that the initial position x, and it will change by an amount v into dt. The reason is v is equal to dx by dt, and that means dx is equal to v into dt. So here we put that. So x plus dx means this only. So this gives us the new position, right? So this, from the old velocity we get the new velocity after dt, and from the old position we get this also. And these steps we have to do several times. So we'll put everything in a while loop, say while t less than, say 5. So that means for 5 seconds we do these operations, okay? And so now let us put this inside the while loop. And so here after this we say t is equal to t plus dt, because next round when you go, you should go with a new timing, right? And now let us do a print statement, say print t, v and x. Alright, so let us run this program. So again, so here you can see it is giving us at a 0.1, it start giving this output, right? And now what we should do is we should see how to plot it instead of printing it. For that, let us make some empty array, say ta. So all the time will be stored. The first element is the initial time, and similarly velocity we make a list, and first element will be the initial velocity, that is 0, and the displacement array is the initial position. And now inside this loop, instead of printing, what we should do is we should add these new elements to, say, time array. We should append the new time. Similarly, the velocity array, we should append the newly calculated velocity, and to the position array we should calculate. So that means every dt we are calculating this new velocity, new position, and go in the loop. And once it comes out of the loop, we can plot the time array versus the velocity array, and also the time array versus the displacement array, and show this. And this should show the sinusoidal variation. Let us save this and run it. So you can see here, this is the graph we are getting. So if you look at the graph, this one is obviously the velocity graph, right? Because our initial velocity is 0, and then the velocity is going in one direction, and initial position you can see it is 2. So then from here the stretched that mass, when we release it, it is coming towards the equilibrium position. When this is becoming the x is becoming 0, velocity reaches a maximum, then it goes, because of this velocity, that momentum, it goes to the other extreme. So then it's keep on oscillating, right? And you also notice that it will go on forever, because there is no frictional forces, that at least we have not included any frictional forces, so that it will keep on going like this. So to make this slightly smoother, we can reduce the value of dt. Suppose make it 0.01, so our result becomes some slightly better. So here, so now as you can see, with time the position also is oscillating between 2 and -2, and velocity is also oscillating. So what will happen if there is some friction, and the force will not be minus kx? Suppose say we put some force, so that is proportional to the velocity, right? Minus say 0.5 into v. A velocity dependent frictional term is added. That means force is this now. Let us see what happens. So now you can see it's gradually coming down. And what will happen if you increase this frictional term? Then the damping will be faster. See, now it is coming down like this. If you much more friction, see, it's coming down very quickly. Within a couple of cycles it's all almost done. And now you can study the effect of the spring constant. Suppose say spring constant you increase. So let us remove this damping term now. And spring constant, without changing anything, let's once again run it. So this is what you see. That means you have here within 5 seconds you have something like say 2.5 cycles. Okay, now if the spring constant is made 50, and when you run it, you find that means there's more cycle. That means if the spring constant is more, it is going to oscillate faster and faster. That is what it shows here. See, more cycles are coming within this given amount of time. And instead of that, if you change the mass from 1 to 3, you can see that number of cycles reduce. That means increasing the mass, the movement becomes slower, so less number of cycles per second. So this is how, with that simple equation, my force is equal to minus k into x, you can just do a simple integration and find out position and velocity as a function of time.